Welcome to qnawire.
So we have a particle moving in one dimension, the x-axis, and it's described by the wave function psi of x is equal to, now this is a piecewise function, so we'll have a e to the negative bx for x greater than or equal to 0, and a e to the positive bx for x less than 0. All right. Now, in this case, b is going to be equal to 2 per meter, and a is going to be greater than 0. So we have some parameters and conditions for this. The first thing we're asked to do is to solve for the normalization constant. We need to find the constant a so that the wave function is normalized. Now, what it means to be normalized is that your integral over all space is going to be applied to the wave function squared, and that needs to be equal to 1. Okay, so for us, in our case, the wave function is going to represent different things in different intervals. For the interval on x less than 0, our wave function is going to be equal to a e to the bx. So that means that the wave function squared, which is equal to the wave function times its complex conjugate, is going to be equal to just the wave function squared. In this case, take a note that there is no complex part to the wave function, it's real. So we just get psi squared, so that'll be a squared e to the 2bx. This is the wave function for the interval x less than 0. For the interval x greater than 0, greater than or equal to, our wave function is going to be represented by a e to the negative bx. So a e to the negative bx has no complex part as well. And if we square this part, instead of the complex conjugate, we will get just psi squared. And so that will give us a squared e to the negative 2bx. So make a note here, it should be squared, and here it should be squared as well. So now we have our two wave functions. The first one is on the interval for x less than 0, and the second one is for the interval x greater than 0 and equal to. The next thing we need to do is figure out the interval for each of our integrals that we're going to take to try to normalize the wave function. In other words, we need to use these two wave functions, put it into the integral of psi squared dx, and set that equal to 1. All right, now, for this case, we're going to have to separate the integral into two different integrals. So actually, I'm going to move it down at the bottom here. And so for this case, we need the integral over all space. In this case, all space is from negative infinity for x to positive infinity. So from negative infinity to 0, in other words, x less than 0, we have the wave function. Psi squared is equal to a squared e to the 2bx. And then for the second part of the integral, over the interval from 0 to positive infinity, we have the wave function psi squared is equal to a squared e to the negative 2bx. Now this needs to be equal to 1. So if we simplify this a little bit, we can take out an a squared. If we go ahead and do the integrals, the first integral will be e to the 2bx over 2bx. And that'll be from negative infinity to 0. And we'll also have e to the negative 2bx over negative 2bx. And that will be from 0 to positive infinity. Now, if we take this integral, we'll find out that two of the terms will cancel out. What we'll get is a squared e to the 0th power is just 1. So from here on out, I'll write e to the 0th powers as 1. 1 over 2b this term in the middle, negative 1 over e to the infinity times 2b, is going to cancel out as 0. It's also going to cancel out with the other one, e to the infinity at the bottom times 2b. Okay, and then the last term is 1 over 2b. So it looks like all of this needs to be equal to 1. So that means that a squared times 2 over 2b, right? 1/2 b and 1/2 b, so that's 2/2 b. So that'll be equal to a squared over b. If this is equal to 1, that means that a must be equal to the square root of b, which is the square root of 2 per meter. And so we'll close out the first part by saying the normalization constant, the constant that makes the wave function normalized, is going to be equal to about 1.41 meter to the negative 1/2. Okay, so this is the first part of our answer. Part A had us find the normalization constant, A, which was equal to 1.41 meter to the negative 1/2. All right. Now, the next part has us to sketch the graph. We can do this pretty quickly. Sketching the graph of the wave function. Again, the wave function is going to be a piecewise wave function. One piece will be a e to the negative bx. The other a e to the positive bx. Positive bx is for x less than 0 interval, and negative bx and the exponential is for x greater than or equal to 0. So when we want to draw the graph, we'll just basically sketch it. We don't have to make it too fancy. We want to note the key points. For example, the y-intercept, where x is equal to 0, needs to be equal to a for both of these. Now, on the interval where x is less than 0, we have a regular exponential function. Usually we'd have something like this. For an exponential function, it's going to be shifted over to the second quadrant for all the x values less than 0, and it's going to hit its peak point here. Remember it at a. It doesn't actually touch at x equals 0, but the other part of the wave function does touch at x equals 0. And so that's going to be a negative exponential, and usually that would look something, we'll draw it in red like this. Again, they cross at 1 exponentials when x is equal to 0. Instead, we will have it come from x equals 0 and shift it over to the first quadrant. And so here's our wave function. Now this kind of brings up a point about symmetry. It looks as if we have a decent amount of symmetry about the y-axis. So we can say that a particle may spend 50% of its time over here and 50% of its time over on the other side. Okay, so this is part B, sketching the graph. Pretty straightforward. After we've sketched a graph of the wave functions, the next thing to do is to find the probability that we can find a particle in specific regions of the wave function. Okay, so we have the wave function again as a piecewise function, a to the negative bx and a e to the positive bx, x less than 0 here, and x greater than or equal to 0 here. Okay, so we know that the sketch shows us that at least 50%, right, is going to be on one side of the y-axis. The other 50% probability is going to be on the other side. Let's go ahead and calculate that. So to calculate the probability, again, p is going to be equal to the integral from all space. Well, in this case, we won't do all space. We'll do the space that we need. Okay, so we'll call that s for now. That's the space that we need to find our probability in. And that will be the same thing as before, the wave function squared for that region. It should equal some probability. We won't set this equal to 1 because we're not trying to find the probability of finding the particle in any place. We're trying to find the probability of finding a particle in a specific place. For this particular question, the first part requires us to find the probability within 50 centimeters of the origin. So if we were to look back at the graph, 50 centimeters within the origin is going to be symmetric. We can imagine that will be something like this, negative 50 centimeters and positive 50 centimeters. We'll see how this works out in the integral, but we'll keep in mind that this is symmetric. So let's set up our probability integral. The probability is going to be equal to the integral from negative 0.5 meter, 0.5 meters positive. The wave function, we'll square that. And now we can use a little bit of symmetry calculus to help us. I'll say that this integral is 2 times the integral from 0 to 0.5, since it's metric. And then I'll take the wave function for this interval, so greater than 0. The wave function for when x is greater than 0 is a e to the negative bx, so we'll say a e to the negative 2bx for a square wave function. And we will solve this. So first step, we'll have the 2 out, a squared, and for our integral, we'll have from 0 to 0.5 e to the negative 2bx. That's going to give us 2a squared over negative 2b. And for the integral part, we have e to the negative 2 times 1/2 for the 0.5 times 2 for b. Okay. And minus e to the 0. So that'll just be 2a squared over negative 2b. The 2's cancel. E to the 1/2 and 2 cancel. So that will give us negative 2 minus 1. And so our final answer that we'll get for the probability will be a squared over b, over negative b, times e to the negative 2nd power minus 1. Now, we can plug in our values. A is equal to the square root of 2, so a squared is equal to 2. B is equal to 2, so negative b is negative 2. E to the negative 2nd power, we'll write that as a fraction, 1 over e squared, minus 1. And since we know that 1 over e squared is less than 1, we'll get a negative number here, and it will cancel out with this negative. So we'll get a positive value of 0.865, which means that there is a probability of around 87% that we'll find this particle within 0.5 meters of the origin. The second part of this question wants us to find the probability of finding this particle on the left side of the origin. So if we're talking about the left side of the origin will have our values of x less than 0. So the equation or the wave function for values of x less than 0 will be psi is equal to a e to the bx, which means our probability will be equal to the integral. Now we want this on the left side of the function, so we'll go from negative infinity, left side of the axis, negative infinity to 0, and that will be the wave function squared, so that will be a squared e to the positive 2bx. Again, we'll calculate this. We won't set it to 1 because we need to figure out what the probability is. And so that will give us the integral. We'll take out an a squared from negative infinity to 0 of e to the 2bx. That gives us a squared Now for the integral, we'll have e to the 0 minus e to the negative infinity. And so e to the negative infinity will drop out. E to the 0 is 1. Don't forget to divide by 2b for the exponential term, for the antiderivative, and then that will be just a squared over 2b. Now, if we plug in a equals square root of 2, so a squared is equal to 2, b is equal to 2 as well, we will get a probability of 1/2. Now that should make sense, because if we look at our function graphed, our wave function, the probability of finding a particle on the left side of the origin is half of the graph for the full wave function. Okay, so this is how the symmetry works out. Now the final part of this is going to ask us to find the probability of the particle existing between 0.5 meters and 1 meter. So now we need x between 0.5 meters and 1 meter. Wave function in this region is a e to the negative bx, and that's for x greater than or equal to 0. So that means our probability will be equal to the integral from 0.5 to 1. And let's see, we will have the wave function squared, e to the negative 2b x dx, a squared over negative 2b. And for the integral part, we'll have e to the negative 2, b is equal to 2, and x in this case will be equal to 1, minus e to the negative 2, b is equal to 2, and x in this case is equal to 0.5 or 1/2. So now we'll have a squared over negative 2b, e to the negative 4th, minus e to the negative 2nd power. Okay, so we have a decent answer here. Putting this into the calculator and evaluating this, we get for a squared, that's going to be 2, and negative 2 times b, which is also 2. I'm going to leave the e's as they are, e to the negative 4th minus e to the negative 2nd. When I simplify all of this, I get 1/2 e to the negative 4th minus e to the negative 2nd power. Right, so we put this in the calculator, we see this is a probability of 0.0585, or we get a probability of 5.85%.